My name is Dimitrios Siakavaras, and in this video I will present our work on adding support for efficient range query operation on concurrent B+ trees that use a synchronization mechanism known as RCU-HTM. The motivation of our work is to provide concurrent B+ trees with correct and efficient range query operations. Range queries are operations that search for keys inside a given range. They are very important in database systems, key value stores, and many other use cases. In serial B+ trees, it is easy to implement efficient range queries, but in concurrent versions of B+ trees, it is very challenging to do so, since range queries typically access a large part of the data structure, and this makes it hard to apply synchronization mechanisms such as locks and lock-free techniques. In our work, we extend an RCU-HTM based B+ tree with range query support. Our range query operation has an easy implementation. It uses a single HTM transaction to atomically read the set of leaves that contain keys in the requested range. At the same time, it provides very high performance, especially for small to medium-sized key ranges, where the transactions that are executed are small, both in terms of memory and in time duration. We validate the high performance of our range query operation by comparing with 6 state-of-the-art concurrent data structures with range query support. RCU-HTM is a synchronization mechanism that combines read-copy-update with hardware transactional memory. With read-copy update, we have updaters work on copies of subtrees rather than directly on the original tree, and in this way readers can proceed without any synchronization. Hardware transactional memory enables the optimistic execution of concurrent updaters, which only roll back their operation when there is a conflict, which means that 2 or more updaters work on the same part of the B+ tree. Update operations in RCU-HTM B+ trees proceed in the following 6 steps. First, a typical traversal of the tree is performed until the appropriate leaf is reached. Then, we perform the necessary modifications on copies of the affected node rather than on the original nodes, and in this way we effectively create a copy of the affected subtree. Also, when copying a node, we keep its current contents in a validation set, which is later used to validate that no other thread has modified the replaced subtree. Then we start an HTM transaction inside which we validate that the nodes to be replaced have not been concurrently modified by another thread, and then we install the newly created subtree by changing a single node's child pointer. This node is called the connection point. Finally, we commit the HTM transaction. Here is an example where we insert key 31 in a B+ tree. The traversal is first performed, and then the subtree copy is created with the modifications applied on copies of the affected nodes. Then we start an HTM transaction, validate that the nodes that are going to be replaced have not been concurrently modified, and then we install the newly created copy by changing the child pointer of the connection point, which here is the root of the tree. Finally, we commit the HTM transaction. In this paper, we extend the RCU-HTM B+ tree by adding range query support, and our range query operation proceeds in the following steps. First, we perform a typical traversal until the appropriate leaf is reached, and then we start an HTM transaction inside which we scan the list of leaves until we reach the last leaf that contains keys in the desired range. During this scan, we only check the max key of each node, and in this way we minimize the memory footprint of the executed transaction, and we store the pointers to all the scanned leaves. Then we commit the HTM transaction, and finally we read all the keys from the scanned leaves. This is safe to do outside the transaction, since RCU-HTM uses copies to modify the keys of a node. and thus the scanned leaves will not change during this final last step. An example range query is shown here. So we first perform the typical traversal of the B+ tree, then we start an HTM transaction and scan the list of leaves until we reach the last leaf that contains keys in the desired range. Finally, we commit the HTM transaction, and then we can safely read the keys from these leaves. Actually, with the HTM transaction, what we did was to atomically take a snapshot of the appropriate leaves. So if another thread concurrently tried to modify, to add or remove a key from the desired range, then the transaction would have aborted and the operation would have restarted from scratch. The advantages of our range query operation are that it is very simple to implement, and it is highly efficient for small to medium-sized ranges when transaction sizes are small. But the disadvantage is that for large-sized ranges, the transactions fail to commit due to hardware limitations. In our experimental evaluation, the hardware that we used was a two-socket Intel server with 2 Xeon processors and a total of 88 hardware threads. Our benchmark is a typical data structure benchmark where a number of worker threads perform random operations on random keys, and we evaluate our implementations under different execution scenarios by varying the mix of operations, the range query size, and the number of threads. We compare against 6 state-of-the-art implementations, which are shown here. On small key ranges, we can see that the throughput of our B+3, of our RCU-HTM B+3 is better than the rest of the implementations on all cases. This is due to the small transactions that our implementation has, and on large ranges with 100k keys, we have still in some cases the best performance, although the scale is not as good as it was in the small key range scenario. To conclude, in this work we have extended an RCU-HTM based B+3 with range query support, with very simple implementation for our range query and high performance, especially for small to medium key ranges. As a future direction, we aim to seek ways to decrease the size of the transactions by splitting the single transaction in multiple ones. Thank you very much.